You stand in front of a mirror every single morning. You comb your hair. You check your teeth. You adjust your collar. It is perhaps the most mundane, repetitive act in human existence. But have you ever actually looked at what is happening? I mean, really looked with the eyes of a child who hasn't been told that's just the way it is? When you raise your right hand, that fellow in the glass, that eerie, silent double, raises his left. If you wink your right eye, he winks his left. The world is flipped. Left becomes right, and right becomes left. It's so simple, a 5-year-old can point it out. But then, here is the question that should make the floor drop out from under your feet. If the mirror is smart enough to flip left and right, why is it so stupid that it can't flip up and down? Think about that. If I rotate a picture 180 degrees, the top goes to the bottom and the left goes to the right. But the mirror, it's selective. It's biased. Your head is still on top and your feet are still on the floor. Why? What is the mirror thinking? Does it know gravity? Does it know which way is up? Most people will give you a quick, sloppy answer. They'll talk about reflection or angles of incidence, using big words to cover up a hole in their understanding. But big words are just a shroud for ignorance. If you can't explain it to a barman or a youngster without using jargon, you don't understand it yourself. To solve the riddle of the mirror, we have to stop looking at the glass and start looking at the very nature of how we trust the physical laws of this universe. We have to understand the avalanche of discovery. You see, to get to the truth of the mirror, we first have to understand how a single correct idea can bowl over 1,000 years of mystery. We have to look at the first great leap in human logic, Isaac Newton and the secret of the falling moon. Before Newton, the world was split in two. There was earthly physics, the messy stuff down here where things break and rot, and there was celestial physics, the perfect divine circles of the stars. People thought they were different worlds with different rules. But Newton had the audacity to suggest that the universe is honest. He suggested that the rules are the same everywhere. Imagine you're sitting in an orchard, an apple falls. Thump. It's a boring event. But Newton asks, why did it fall? Because the earth pulled it. Okay, simple enough. But then he looks up and sees the moon hanging in the sky. If the earth pulls the apple, does it pull the moon? And if it pulls the moon, why doesn't the moon fall down and hit us on the head? Wait, here is the stroke of genius. Newton realized the moon is falling. It's falling right now. Let's look at the numbers, because the beauty of the truth is always in the arithmetic. Galileo had already measured that near the Earth's surface, an object falls 16 feet in its first second of flight. Now, the moon is about 240,000 miles away. The radius of the Earth is about 4,000 miles. That means the moon is 60 times farther from the center of the Earth than the apple is. Newton suspected that the pull of gravity gets weaker as you move away specifically, that it follows an inverse square law. If you move twice as far away, the pull is 4 times weaker. If you move 60 times farther away, the pull should be 60 times 60, which is 3,000, 600 times weaker. So if the apple falls 16 feet in 1 second, the moon should fall 1/3,600th of that distance. 16 feet is 192 inches. Divide 192 by 3,600, and you get about 0.05 inches, about 1/20th of an inch. Newton sat down and calculated how much the moon's path actually curves in 1 second as it orbits the Earth. He used the moon's speed and its distance, and the answer he got was 1/20th of an inch. Think about the shiver that must have gone down his spine. The same invisible hand that pulls the apple to the dirt is the hand that reaches across the vacuum of space to guide the moon in its path. It was an avalanche of discovery. Suddenly, the heavens weren't a separate magical realm. They were a mechanical system governed by the same jiggling and pulling as the atoms in your teacup. This confidence, this realization that the universe follows strict geometric and mathematical rules is the only way we can begin to tackle the mirror, because the mirror isn't a magical portal. It's a physical interaction between light and matter. And if the mirror flips left to right but not up and down, it's not because the mirror is choosing a direction. It's because our human brains are misinterpreting the geometry of the in and out dimension. The mirror doesn't flip left-right. It flips front to back. It's a depth inversion. When you point north, your reflection points north. When you point up, your reflection points up. But when you point at the mirror, pointing in your reflection points out. We are the ones who label it left and right because we imagine walking into the mirror, turning around, and standing in the place of our double. But in doing that imaginary turn, we are the ones who flip the left and right. The mirror just sits there, obeying the laws of reflection, doing exactly what the geometry demands. But why do we find this so hard to grasp? Why is our intuition so fragile that a simple sheet of silvered glass can trick us? To find out, we have to look deeper into the nature of light and the experiments that eventually broke Newton's perfect clockwork universe. So we've established that the mirror is a depth inverter, not a left-right flipper. It's a geometric trickster that obeys the in and out law. But this brings us to a much deeper, much more unsettling mystery. If the mirror is just reflecting light back at us, what exactly is light? And how does it carry information across that empty space so fast that we never see the delay? To Newton, light was like a stream of tiny bullets, or maybe a wave in some invisible ether. He lived in a world of absolute space and absolute time. He thought there was a giant master clock in the center of the universe, ticking away the seconds for everyone, everywhere, at the same rate. It was a beautiful, comfortable, clockwork dream. But then, light started behaving in ways that Newton's bullets simply couldn't explain. Light started showing us that the absolute was an illusion. It began with a man named Roemer back in 1676. He was looking at the moons of Jupiter, specifically Io. Now, Io is like a cosmic clock. It ducks behind Jupiter and pops out at very regular intervals. Roemer noticed something peculiar. When the Earth was moving toward Jupiter in its orbit, the pops happened a little sooner than expected. When Earth was moving away, the pops were late. Wait, think about that. If time is absolute, the clock shouldn't care where the observer is. Roemer realized that the pops weren't late. The light was taking longer to travel the extra distance. He used this to make the first real estimate of the speed of light. It wasn't infinite. It was a number, a huge number, about 186,000 miles per second, but a finite one. This was the first crack in the absolute. It meant that now is a relative term. When you look at your reflection in the mirror, you aren't seeing yourself as you are now. You are seeing yourself as you were a billionth of a second ago. The light had to jiggle from your face, hit the glass, and jiggle back to your eye. Information takes time. But then came the real brain breaker. In the late 1800s, two fellows named Michelson and Morley decided to measure how fast light moves when the Earth is rushing through space. Think about it like this. If you're on a train moving at 50 miles per hour, and you throw a ball forward at 10 miles per hour, someone on the ground sees the ball moving at 60. Simple addition, right? Newton's logic. They expected light to do the same. If Earth is moving into the light, it should seem faster. If we're moving away, it should seem slower. They built this incredibly sensitive machine, an interferometer, to catch the difference. And they found nothing. Absolutely nothing. The speed of light was 186,000 miles per second, no matter how fast they were moving. It didn't matter if they were going toward it, away from it, or sideways. The universe was refusing to add the numbers. It was as if the train was moving at 50, the ball was thrown at 10, but the person on the ground still only saw the ball going 10. This is where the avalanche really starts to pick up speed. This nothing result was the most important discovery in the history of physics, because it meant that the absolute was dead. If light speed is constant for everyone, then something else has to give, something else has to bend to keep the math honest, and that something was time and space themselves. Think about the mirror again. You think of the distance between you and the glass as a fixed, solid thing. But Einstein, taking the torch from where Roemer and Michelson-Morley dropped it, realized that if light is the master of the universe, then space and time are just its servants. They contract and dilate just to make sure light always moves at the same speed. This leads us to a terrifying conclusion about the reflection you see every morning. You are not just seeing a flipped version of yourself. You are seeing a localized interaction of electromagnetic fields that are governed by a speed limit that defines the very structure of your reality. The in and out flip of the mirror is just the surface. Beneath it lies a world where space can shrink and time can stretch, all because light refuses to obey the simple addition of our common sense. But why does light have this special status? Why does the jiggling of an electron in your skin create a ripple that the entire universe has to rearrange its clocks for? To answer that, we have to go beyond the bullets and the waves. We have to look at the layers of reality, the physical, the mind-breaking, and the cosmic. Now we're getting into the deep water. We've seen the mirror flip us inside out, and we've seen light refuse to obey the simple laws of addition. But why? To truly understand the why, we have to peel back the skin of the world like an onion. We have to look at the three layers of reality that Feynman that I have spent a lifetime trying to map. Layer one, the physical action. When you look into that mirror, you think you are seeing yourself, but in the physical layer, there is no you. There is only a staggering number of atoms, roughly $7 times 10, $27 of them jiggling in a very specific organized dance. The electrons in the atoms of your skin are being hit by photons from the light bulb. These electrons soak up that energy and then immediately spit it back out. It's a game of catch played at the speed of light. When these photons hit the silver atoms behind the glass of the mirror, they don't just bounce like a ball off a wall. That's too simple. The photons cause the electrons in the metal to vibrate, creating a collective sloshing of electrical charge. This sloshing creates a new electromagnetic wave that travels back toward your eye. The reflection is actually a brand new wave, born from the coordinated jiggling of millions of electrons in the mirror's surface. Layer two, the mind break. Here is where your intuition starts to scream. Remember the in and out flip? If the mirror flips front to back, it means your reflection is actually a version of you that cannot exist in three-dimensional space without being broken. Think about a glove. If you have a right-handed glove, you can rotate it, move it, or flip it all you want in 3D space, but it will never fit your left hand. It is chiral, it has a handedness. But a mirror takes that right-handed glove and turns it into a left-handed one. It performs a parity inversion. This is the mind break. The mirror isn't just showing you a picture. It is showing you a world with a different mathematical sign. In the 1,950 seconds, we thought the universe didn't care about left or right. We thought parity was conserved, that the laws of physics were the same for us and our mirror doubles. But then we looked at the weak nuclear force, the force responsible for radioactive decay, and we found out the universe is left-handed. It does care. Our mirror selves would actually behave differently in certain nuclear reactions. The mirror isn't just a toy. It's a window into a fundamental asymmetry in the laws of nature. Layer three, the cosmic connection. Wait, let's go even deeper. Why does light jiggle at all? Light is an electromagnetic wave, a ripple in the field. And here is the genius logic that ties it all together. Light is what happens when the electric field and the magnetic field play leapfrog. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. They sustain each other, pushing each other through the vacuum at that magical speed of 186,000 miles per second. This field isn't just somewhere, it is everywhere. You are moving through a sea of fields right now. When you move your hand, you are slightly disturbing the fields that stretch to the end of the universe. The reason the mirror flips front to back is because the electromagnetic field is a vector field. When the wave hits the mirror, the part of the electric field pointing into the mirror is canceled out and reversed by the electrons in the metal. It's a perfect mathematical symmetry dictated by the Maxwell equations. The mirror doesn't flip left and right because the left, right, and up-down axes are parallel to the mirror's surface. The field ripples along those axes aren't forced to turn around. Only the axis pointing into the glass is challenged. The mirror is a force field wall that only reflects the component of the wave that tries to penetrate it. So you see, the mirror isn't a mystery of optics. It's a mystery of geometry and fields. It's a demonstration of how light interacts with the electron sea of matter to preserve the symmetry of the electromagnetic field. You are seeing the math of the universe written in silver and light. But does this math actually hold up in the real world? Can we prove that space and time are this flexible, or that the jiggling of fields is the real truth? To find the proof, we have to look at the clocks on our satellites and the strange particles that rain down from the sky. You might be sitting there thinking, Feynman, this is all very poetic, fields playing leapfrog, mirrors flipping depth, invisible gnats in a stadium, but how do we know it's true? In science, if it doesn't match the experiment, it's wrong. It doesn't matter how beautiful your guess is or how smart you are. So let's look at the evidence. Let's look at the ghost proof. If I'm right, and space and time are actually bending just to keep the speed of light constant, then we should be able to see it, and we do. Every single day, right in your pocket. Think about your GPS. There are satellites whizzing around the Earth at about 14,000 kilometers per hour. According to Einstein and the math that grew out of that Michelson-Morley disaster, because those satellites are moving fast, their clocks should tick slower than ours by about 7 microseconds a day. But it gets weirder. Because they are farther away from the Earth's mass, gravity is weaker up there. And gravity also warps time. That makes their clocks tick faster by about 45 microseconds a day. If we didn't account for these tiny, mind-breaking shifts in time, your GPS would be off by 10 kilometers in a single day. The fact that you can find a pizza joint in a city you've never visited is living, breathing proof that time is not absolute. It is proof that the jiggling of light and the warping of space are the hard, cold reality of our existence. But there's an even more beautiful proof, one that comes from the stars. It's the story of the muon. A muon is like a heavy, unstable cousin of the electron. It's born high in our atmosphere when cosmic rays slam into air molecules. These muons are moving at 99.9% the speed of light, but they have a very short life. They decay, they pop out of existence in about 2 microseconds. Even at nearly the speed of light, a muon should only be able to travel about 600 meters before it dies. It shouldn't even get close to the ground, and yet we see them. We catch them in detectors on the surface of the Earth all the time. How? From our perspective, the muon is moving so fast that its internal clock slows down. It lives longer because its time is stretched. But think about the muon's perspective. From the muon's point of view, its clock is normal, but the distance it has to travel, those 10 kilometers of atmosphere, shrinks. The space itself contracts. The muon reaches the ground because the universe literally moves the goalposts to keep the speed of light honest. Now, let's bring it back to that mirror in your bathroom. When you look at that reflection, you aren't just seeing a face. You are seeing a testament to the honesty of nature. You are seeing a depth-inverted image created by the leapfrogging of fields. You are seeing a version of yourself that obeys a left-handed nuclear force you can't even feel. You are seeing a delay in time so small it's almost zero, but so significant that it defines the limit of how fast anything in this universe can ever happen. The mirror tells us that we live in a world of symmetry, but also a world of profound rules. The reason it doesn't flip up and down is because the universe is a geometric stage, and we are the ones who get confused about which way we're facing. The mirror doesn't care about your labels. It only cares about the in and out. It only cares about the truth. I've spent my life trying to understand these rules, and what I've found is that the more you look, the more beautiful it gets. Nature has this enormous imagination. She takes a simple thing, a jiggling charge, and she builds light and magnets and mirrors and the very structure of time and space. We are like kids playing with a chessboard, and we finally figured out how the pawns move. We figured out the mirror. We figured out the falling moon. But the game is vast. and the pieces are still moving. The truth isn't the destination. It's the thrill of the chase. It's the avalanche of discovery that happens when you stop accepting that's just the way it is and start asking why. So the next time you stand in front of that glass, don't just check your hair. Look at that ghost on the other side. Realize that you are a collection of fields and energy, reflecting off a sea of electrons in a universe that is far more strange and far more wonderful than anything we could have ever invented. The great chessboard is waiting. Are you ready to make the next move?